In today's lesson, I am going to introduce the concept of matrix and use matrices to solve systems of equations. As we solve the systems, I will be telling you about particular types of matrices, such as matrices in row-reduced form, matrices in echelon form, matrices that result from homogeneous equations. Just as importantly as knowing how to solve systems of equations using matrices is the terminology. So make sure you get the terms down. As always, take careful notes as you view the tape, and if you do not understand anything, be sure to get someone to help you. A matrix is a rectangular array of numbers. A M by N matrix has M rows and N columns. So the first letter tells you the number of rows. The second letter tells you the number of columns. So an M by N matrix has M rows and N columns. The element in the ith row and jth column is denoted by Aij. So the small letter denotes an entry in the matrix. The subscripts tell you the row and the column. So I want the entry in the ith row and the jth column. Here we have a matrix. A matrix is a rectangular array of numbers. So we have the matrix 2, 4, negative 3, 6, 3, 0, 1, 2, 4, 2, 0, 8. The matrix is 3 by 4. We have 3 rows, 4 columns. So it's a 3 by 4 matrix, 3 rows by 4 columns. The element in the second row, third column, is 1. So we have A sub 2, 3. That means I want the entry in the second column, means second row, third column. Second row, third column. We get 1. So the entry in the second row, third column, is 1. Two matrices having the same dimensions are equal if and only if corresponding elements are equal. In other words, matrix A is equal to matrix B if and only if, and IFF means if and only if, A sub ij is equal to B sub ij for all elements in the two matrices. So corresponding entries must be the same for the matrices to be equal. Now I'm going to introduce another concept, not equality, but that of row equivalent. Two matrices are row equivalent, and that's what we're defining. if one can be obtained from the other by the elementary row operations. So two matrices are row equivalent if one can be obtained from the other by the elementary row operations. We have three elementary row operations. First, you can interchange two rows. You can multiply a row by a non-zero constant. You can add a multiple of a row to another row. So those are your row operations. So these three elementary row operations: interchange any two rows, multiply any row by a non-zero constant. So I'm going to put in here C cannot be 0, so your constant cannot be 0. You can add a multiple of a row to another row. So as long as you only use these three operations to transform the matrix, then the matrix that you end up with will be row equivalent to the matrix that you started with. One can use matrix notation to shorten Gaussian elimination. As we go through and use the row operations, you will see that they're the same as the equation operations that we discussed in tape 1. One can use matrix notation to shorten Gaussian elimination. Let's solve x minus 2y plus 3z is equal to 9. The opposite of x plus 3y is equal to negative 4. 2x minus 5y plus 5z is equal to 17. Now first of all, we're going to create a matrix of the coefficients. So we have the matrix of the coefficients. The coefficient of x is 1. So my matrix entry is 1. The coefficient of y is negative 2. So the matrix entry is negative 2. The coefficient of z is 3. And then the constant is 9. The negative 1. The 3. There is no z, so that would be 0z. The constant is negative 4. 2, negative 5, 5, and 17. Now many times you'll see a line, kind of a broken line, down to separate the coefficient entries from the constants. See, these were your coefficients, here's your constants. I'm going to use the matrix operations, the row operations, to reduce the matrix. So with the matrix, the first thing I'm going to do is simply add row 1 to row 2. Now the row operation actually says multiply a row by constant and add it to a second row. So actually, you get down technically, I'd multiply the first row by 1 and add it to row 2. We'll leave everything else the same. If I add row 1 to row 2, leave row 1 the same, but I'm going to add row 1 to row 2. 1 plus a negative 1 is 0. A negative 2 plus 3 is 1. 3 plus 0 is 3. 9 plus negative 4 is 5. And I still have 2, negative 5, 5, and 17. Now this matrix is row equivalent to the top matrix. Not equal to it, but it's row equivalent to it. Now I'm going to multiply row 1 by -2 and add to row 3. So I'm going to multiply row 1 by -2, add to row 3. Again, that's a legal operation. Multiply any row by constant, add to the other row. And I'm coming up here for that one. So multiply row 1 by -2, add to row 3. So that means I'm not changing rows 1 or 2. So I'll just recopy those. 1, -2, 3, and 9. 0, 1, 3, and 5. And now I'm going to multiply row 1 by -2, add to row 3. 1 times -2 is -2. -2 plus 2 is 0. -2 times -2 is a +4. A +4 times a +4 plus a -5 is -1. 3 times -2 is -6. -6 plus 5 is -1. -2 times 9 is -18. -18 plus 17 is -1. Now there is a method to what I'm doing. There is a reason for it. What I'm trying to do is to make the first column have a 1 and all the rest zeros. So I'm trying to create a matrix in which I have 1s along the diagonal and I have zeros below it. That's what I'm trying to do. So my goal is to have 1s along the diagonal, zeros below it. Well, I have a 1 here. I'd like to have a 0. All I have to do to get a 0 in this position is to add row 2 and row 3. So we're going to add row 2 to row 3. One, -2, 3, and 9. 0, 1, 3, and 5. Now if I add row 2 to row 3, 0 plus 0 is 0. 1 plus a -1 is 0. 3 plus a -1 is 2. 5 plus a -1 is 4. Now I'm going to multiply row 3 by 1/2. So I have the matrix 1, -2, 3, 9, 0, 1, 3, 5. Now multiply it by 1/2. 1/2 times 0 is 0. 1/2 times 0 is 0. 1/2 times 2 is 1. 1/2 times 4 is 2. So I have achieved my goal of having 1s along the main diagonal and 0s below it. Now this matrix is now called row echelon form. Now row echelon form is when I have all 1s or 0s on the main diagonal and any zeros come at the end, and below the main diagonal, all zeros. So it could be 1, 1. This could be 0 now. Let's go all ones on the main diagonal, ones or zeros. And any zeros come at the end of it. And then below the main diagonal, all zeros. That's row echelon form. Now once you get the matrix in row echelon form, it's very easy to go back and create the equations to back substitute and get the solution. Because remember, this is 0x, 0y, and 1z. So I see here that 1z is equal to 2. So I have z is equal to 2. This is going to be 0x plus 1y plus 3z is equal to 5. Or I get y is equal to 5 minus 3z. Well, z is 2. 3 times 2 is 6. 5 minus 6 is negative 1. So y is negative 1. The top equation is x minus 2y plus 3z is equal to 9. Or I have x is equal to 9 plus 2y minus 3z. So I have x is equal to 9, y is negative 1, 2 times negative 1 is negative 2, z is 2, 3 times 2 is 6, that would be minus 6. So x is, 9 minus 2 is 7, x is 1. So we have the solution, x is 1, y is negative 1, z is 2. Now let's go back to the matrix in row echelon form. So we have 1, negative 2, 3, 9, 0, 1, 3, 5, 2, negative 5, 5, and 17. This matrix is in row echelon, I'm sorry, no, I copied down the wrong one. This matrix is not row echelon form. The one that was row echelon form was 1, negative 2, 3, and 9, 0, 1, 3, and 5, 0, 0, 1, and 2. So that was row echelon form. If we continue and create zeros above the main diagonal as well, we have what's called reduced row echelon form. So if I continue with the reduction process and have zeros above the main diagonal, I get reduced row echelon form. If I can do that, my first step would be multiply row 2 by negative 2, add to row 1. So leave row 2 and 3 the same, 0, 1, 3, 5, 0, 0, 1, 2. I'm going to multiply row 2 by negative 2 and add to row 1. Negative 2 times 0 is 0. 0 plus 1 is 1. Negative 2 times 1 is negative 2. Well, in order to make that 0, I don't need to multiply by negative 2. I need to multiply by positive 2, because I want a 0 there. So positive 2 times 0 is 0. 0 plus 1 is 1. A positive 2 times 1 is a positive 2, plus a negative 2 is 0. 3 times 2 is 6. 6 plus 3 is 9. 2 times 5 is 10. 10 plus 9 is 19. So I multiply row 2 by positive 2, add to row 1. Now, I'm going to worry about column 3. I've got columns 1 and column 2 okay. I'll worry about column 3. I need a 0 here and a 0 here. Well, what I can do is I can multiply row 3 by -3, add to row 2. A -3 plus 3 is 0. Then I can multiply row 3 by -3 and add to row 1. So I'm going to do them both at the same time. So row 3 is 0, 0, 1, and 2. Now I'm going to multiply row 3 by -3. So you multiply row 3 by -3, add to row 2. Then I multiply row 3 by -9 and add to row 1. But first of all, I'm going to multiply row 3 by -3 and add to row 2. -3 times 0 is 0. 0 plus 0 is 0. -3 times 0 is 0. 0 plus 1 is 1. -3 times 1 is -3. -3 plus 3 is 0. -3 times 2 is -6. -6 plus 5 is -1. Now I'm going to multiply row 3 by -9. Get rid of that 9. Add to row 1. -9 times 0 is 0. 0 plus 1 is 1. -9 times 0 is 0. 0 plus 0 is 0. -9 times 1 is -9. -9 plus 9 is 0. 2 times -9 is -18. -18 plus 19 is 1. Now this is called reduced row echelon form. So we have reduced row echelon form in which we have ones along the diagonal and zeros both above and below. If you take it all the way to row reduced echelon form, then the solution is obvious. We have 1x is equal to 1. So that's 1x, 0y, 0z. 1y is equal to a -1, and 1z is equal to 2. Solve x plus 3y plus z is equal to 0. X plus y minus z is equal to 0. X minus 2y minus 4z is equal to 0. Now what we have here is a homogeneous system. I know it's homogeneous when I have all zeros as my constants. That's the definition of a homogeneous system. The constants are all zeros. So if you have a system of equations in which the constants are all zeros, the system is said to be homogeneous. Now obviously, x equals 0, y equal to 0, and z equal to 0 is a solution. Or we have 0, 0, 0. Obviously that would be a solution because 0 plus 0 plus 0 is 0. 0 plus 0 minus 0 is 0. 0 minus 0 minus 0 is 0. So we have the trivial or the obvious solution, 0, 0, 0. Do we have other solutions? Well, let's solve it and see. I'm going to write it in matrix form. 1, 3, 1, 0, 1, 1, -1, 0, 1, -2, -4, 0. So to write it in matrix form, I simply use the coefficients. All ones in the first column, 3, 1, negative 2 in the second column, 1, negative 1, negative 4 in the third column. I want to get to at least row echelon form, in which I want all ones along the main diagonal, or zeros, ones or zeros on the main diagonal, with the zeros coming at the end, and all zeros below it. Well, the first row is okay, so I'm going to rewrite the first row, 1, 3, 1, 0. And now, to get these columns, in both cases, I'm going to multiply row 1 by negative 1 and add to row 2, then row 3. So one of the row operations is to multiply a row by a constant, add to another row. 1 times negative 1 is negative 1. Negative 1 plus 1 is 0. 3 times negative 1 is negative 3. Negative 3 plus 1 is negative 2. 1 times negative 1 is negative 1. Negative 1 minus 1 is negative 2. 1 times 0 is 0. 0 plus 0 is 0. Now I'm going to multiply row 1 by negative 2 and add to row 3. By negative 1, I'm sorry, and add to row 3. 1 times negative 1 is negative 1. Negative 1 plus 1 is 0. 3 times negative 1 is negative 3. Negative 3 minus 2 is negative 5. 1 times negative 1 is negative 1. Negative 1 minus 4 is negative 5. Negative 1 times 0 is 0. 0 plus 1 is 0. Now I'm going to multiply row 2 by negative 1/2, row 3 by 1/5. Now that's legal because I can multiply row by a constant. Now the reason I'm multiplying row 2 by negative 1/2 is to get a 1 here, because I need ones along the diagonal. You'll see in a minute why I'm multiplying row 3 by 1/5. 1, 3, 1, 0. Negative 1/2 times 0 is 0. A negative 1/2 times a negative 2 is a positive 1. A negative 1/2 times negative 2 is a positive 1. A negative 1/2 times 0 is 0. Now I'm going to multiply row 3 by 1/5. 0 times 1/5 is 0. Negative 5 times 1/5 is negative 1. Negative 5 times 1/5 is negative 1. 0 times 1/5 is 0. Now for row echelon form, I need a 0 here. Well, all I need to get a 0 is to add rows 2 and 3. So add row 2 to row 3. So 1, 3, 1, 0, 0, 1, 1, 0. Now add row 2 to row 3. 0 plus 0 is 0. 1 plus a negative 1 is 0. 1 plus a negative 1 is 0. 0 plus 0 is 0. Now this is in row echelon form. The main diagonal has all ones or zeros, with zeros at the end, and there are zeros below the main diagonal. Notice in this case, this is going to be equivalent to having 0 is equal to 0, because 0x plus 0y plus 0z is equal to 0. When I have a true condition like this, then that means we have many solutions. So we do have more than just the one solution. Going back to this equation, I have that y plus z is equal to 0. Which means that y is equal to the opposite of z. According to this equation, I have x plus 3y plus z is equal to 0. So I have x plus 3 times, but y is negative z, plus z is equal to 0, which gives me x minus 2z is equal to 0, because that would be negative 3z plus 1z is negative 2z, or I get x is 2z. So I can write my answer in parametric form by let z is equal to the parameter t. Then y would equal to the opposite of t. X would equal to 2t. So my solutions would be of the form 2t, the opposite of t, t. So I can write it in set notation instead of all ordered pairs, ordered triples, 2t, opposite of tt, such that t is a real number. Well, we see 0, 0, 0 is in there, because if I let t be 0, 2t is 0, the opposite of t is 0, it's t 0. So 0, 0, 0 is one of many solutions. A natural tendency might be for you to say, I can already solve equations by Gaussian elimination, therefore I do not need to worry about the matrix row operations. That would be a terrible mistake. Using the elementary row operations for matrices will be a major part of the course. We'll be using the elementary row operations for many other purposes as the course continues. If you do not understand how to use the elementary row operations to write a matrix in both row echelon and reduced row echelon form, be sure to get help.